Hello, in this video I want to look at the Taylor polynomial of arctangent. Now we have that the formula for a Taylor polynomial of the nth degree is going to be given by Pn of x equal to the series summation from k equals 0 to n, and then we have the kth derivative at a divided by k factorial times x minus a to the k. Now, if we wanted to look at, say, for example, just what's happening with the expansion, basically you have that this would be f of a plus f prime of a, but now you're going to multiply this by x minus a to the first power, and all of this is divided by 1 factorial. Plus, so you repeat that process of finding the next term, of which this will be divided by 2 factorial, and this will be times x minus a squared. And essentially you just keep repeating that until you get to the nth derivative of your function at a, and you're dividing this by n factorial, and you have x minus a to the nth power. Now, if we look at the arctangent function, basically what we want to do is take f of x equals to tangent inverse of x, and for this one let's go ahead and use that we're going to center it at 0. Now for purposes of the example, let's just take perhaps like just a few of the first terms of arctangent. So I know that I need my function value, which in either case is just going to be 0 when we plug that in. So we go ahead and we find the first derivative, which in this case would be 1 over x squared plus 1. But if we plug in the 0 into that equation, basically you're just going to get 1. Now, if we go ahead and we take the second derivative, then in that case we have that that's going to be negative 2x divided by x squared plus 1 to the second power. But when you plug in the 0, you get that that's just going to be 0. Now, basically from there, you would have to take the third derivative using quotient rule. So if we use the quotient rule, then in this case, you're going to have x squared plus 1 squared multiplied by, okay, so the derivative of this is going to be negative 2 minus 2 times x squared plus 1, but then multiply by basically 2x, because you have the derivative of x squared plus 1 is 2x, but essentially this is going to be multiplied by the negative 2x that we started with, so we have that that would be times negative 2x. Now all of this is divided by essentially x squared plus 1 to the fourth power, because we're essentially using just quotient rule. So from here we see that when we factor the x squared plus 1 out, we have that that's going to be negative 2 times x squared plus 1. And then from there, I notice that essentially I have a negative 2 times 2x times negative 2x, which that's going to give us 8. So we have that that's going to be not minus, but plus 8 plus 8x squared. Now from there, we have that we would just divide this by the same thing, x squared plus 1 to the fourth power. But when we go ahead and we basically simplify this a little, because I see that one of the factors of x squared plus 1 will cancel out, and it's going to leave us with a third power, that we're going to end up with 8x squared minus 2x squared, and then minus 2. And all of this is divided by x squared plus 1 to the third power. Now simplifying this a little further, we have that that's going to be 6x squared minus 2 divided by x squared plus 1 to the third power. So if we plug in 0 into this equation to the third derivative, okay, so we have f3 of 0, that's going to be equal to basically negative 2. Okay, so let's say that we wanted to just go ahead and use essentially just the third degree polynomial for arctangent. In that case, you would have that this would be p3 of x equals to the series summation from k equals 0 to 3, and then we have k of, in this case it's centered at 0, so we know that it's going to be at 0, and then we have that this would be divided by k factorial, and then we have that this would be times basically not necessarily x minus 0, but x to the k. Now, when we go ahead and we do our expansion of the Taylor polynomial for arctangent, basically what you're going to get is the following. So we have that the f of 0 was 0. So we have that that was going to be f of 0 plus f prime of 0 divided by 1 factorial. And then we have plus the second derivative, and we'll just use that notation, divided by 2 factorial. And then we have that this will be basically the third derivative. Okay, so we have the third derivative at 0, and this is all divided by 3 factorial. And yeah, we forgot some x's, so x squared, and x cubed. Now, when we go ahead and we plug this in, basically, and we'll switch to using this, so we have 0 plus, okay, so this is going to be 1 times x divided by 1 factorial plus, okay, so we did find that the second derivative at 0 was 0 divided by 2 factorial, and that's times x squared plus the third derivative. Now the third derivative was negative 2, so we have negative 2 divided by 3 factorial, and that's going to be x cubed. Now notice that basically if you simplify this, this is going to be x, and then it's going to be minus 1/3 x cubed. So in either case, this is the third degree Taylor polynomial for arctangent. Okay, so we have that this is going to be our polynomial, and if we were to generalize this basically for the arctangent function, basically you would find that the nth degree of your polynomial for arctangent would be equal to the series summation from k equals to 0 to n. And check this out. Well, in either case, like if we were going to use that we're just plugging in 0 into the nth derivative for arctangent, basically we would find that this would give us so see like how you have a 1 and then you have a negative 1. So essentially we're going to have negative 1 to the k, but then notice that here this is divided by 1. So it's going to be divided by 2k plus 1, but then notice that this is to the 1 and this is to the third power. Now what that means is that essentially it's going to be powers of x that are odd. So you have 2k plus 1. So essentially this is the nth degree polynomial for arctangent of x. Okay, so this is actually kind of useful in regard to, say for example, like if you were trying to estimate a specific value of arctangent, because for example, let's say that you wanted to estimate arctangent inverse of 1. Well, I essentially know that the exact value of this is pi over 4. But what that means is that using the Taylor polynomial, where you have that pi over 4 would equal to p sub n of 1, and that would equal to the series summation from k equals 0 to, not infinity, I apologize, that would be to the nth degree, and that would leave you with negative 1 to the k divided by 2k plus 1. Now, essentially, you've learned at this point that this is a conditionally convergent series, but in either case, this is going to be your approximation for pi over 4 if we choose n to be whatever we want it to be to estimate, pi over 4. But interestingly enough, basically, if I was to multiply this by 4, then I would actually be, like if I multiply by 4, I would actually be estimating basically pi using the same series essentially. So in that case, that's pretty useful. But you'll notice that if you try to substitute this into your third degree polynomial back over here, that essentially if you plug that in where you take 4 and you multiply by p3 of 1, essentially you're just taking 4 times 1 minus basically 2/3, which in this case, let's see, yeah, well, 1 minus a third actually. So 1 minus a third, which would be approximately 2.67, which we know is not anywhere close to what pi actually happens to be. But if we were to extend it, like let's say to the 10th degree, then we might actually be able to approach pi a little bit better. But interestingly enough, pi, it just keeps going. So how do we actually know how far that we can estimate pi to? In that case, if it never ends in either case, and that has actually do with the remainder theorem that we learned in class.